Hi, hello, good evening. So for today, we will be discussing the second type of transistor, which is the field effect transistor. So the previous videos are all about bipolar junction transistor. So for today, we will be discussing the second type of transistor, which is the field effect transistor. So what is the difference? What is the main difference between the BJT and FET? So we will be discussing it for today. Okay, so FET, the acronym FET stands for Field Effect Transistor. So just like the BJT, it is also a three-terminal device. So since it is a transistor, so it has three terminals. But unlike the BJT, which is bipolar, so FETs are unipolar. So later on, upon discussing the characteristics of your FET, we will be defining why is it called unipolar. Okay, so this is a three-terminal unipolar solid-state device in which current is controlled by an electric field as is done in vacuum tubes. Now, when we say electric field, what comes into your mind? So electric field are sometimes goes with electric field, sometimes goes with EMFs or voltages. So the main difference between FET and BJT, so the first thing is BJTs are bipolar devices while FETs are unipolar devices. Another thing is that FETs are voltage controlled devices, whereas for BJTs, they are said to be current controlled devices. So those are the two main difference between FETs and BJT. Okay, so we have discussed in BJT that it has two types, which is the NPN and the PNP. In FET, so the family of FET is larger or bigger compared with the BJT, because BJT it only have the NPN and the PNP, while for FETs, so we have two types of FETs. So we have JFET and MOSFET. So the JFET, it stands for junction field effect transistor, while MOSFET, it stands for metal oxide semiconductor field effect transistor. But it doesn't stop there. Okay, so these are the different types of FETs. As you can see, they have furthermore, so JFETs are furthermore divided into two. So we have the N channel JFET, and we have the P channel JFET. So upon looking at the symbol, so you can differentiate, or you can see the difference between an N channel and the P channel through its gate. Okay, so usually the arrow is pointing where your N-type material is. So this is your N channel and this is your P channel. Whereas for MOSFET, so in some other references, in usually old references, instead of using MOSFET, which is metal oxide semiconductor, you can find it as IGFET. Okay, so what does IGFET stands for? So IGFET stands for insulated gate field effect transistor. So we later on, as we discuss their physical characteristic, we will see why it is called an insulated gate field effect transistor. Okay, so under MOSFET, it has two more types. So we have the D MOSFET and we have the E MOSFET. So sometimes we do not include the term only. So it is just E MOSFET, while in this case, sometimes it is just called D MOSFET. So without the E. But the main difference here is, so the D stands for depletion and the E stands for enhancement. So for the D MOSFET, it functions both in the depletion and in the enhancement mode, while E MOSFET they only function at the enhancement mode. So what is depletion mode, what is enhancement mode, we will try to find that out later. So under the D MOSFET, okay, we have two more types. So we have the N channel, we have the N channel, and we have the P channel D MOSFET. And also for the E MOSFET, we have the N channel and the P channel. So as you can see, the difference between the JFET and the MOSFET is that the gate is separated. Okay, so the FET has the three terminals. It is the drain, the source, and the gate. So the gate, as you can see, is separated. So as you looking at the symbol, so it is separated with the drain and the source. So this is the main difference between the N channel and the P channel. So that also comes with the name insulated gate, because the gate is not totally connected with the drain and with the source. For E MOSFET, so what is the difference in the symbol? As you can see, the drain and the source is not totally connected. So as you can see, they are being connected by a broken lines. So that's the main difference between the D MOSFET and the E MOSFET. But both of them, the gates are insulated. Okay, so all in all, we have 6 types of FETs. Okay, so 2 for JFETs and 4 for MOSFETs. Okay, so let us go for with the basic construction of JFET. So we will be starting with JFETs. So the basic construction, it can be fabricated with either an N channel or a P channel. So if you can still remember, we have two types of extrinsic semiconductor. So we have the N type and the P type. So if we wanted to construct an N channel JFET, we will just be getting strip of an N channel or an N type material. Or if you wanted to have a P channel, we will be using the P strip of a P type semiconductor. Okay, so although N channel is generally preferred, since when you performed the experiment regarding JFET, it is harder for us to look for a P-channel devices, right? So mostly we use an N-channel. Although after we analyze the N-channel, the analysis for P-channel is just the same. All we have to do is just to reverse the polarities of your sources and also reverse the direction of your current. So that is the only difference. So let us discuss how are we going to fabricate an N-channel JFET. So for fabricating an N-channel JFET, first, we are going to get a narrow bar of an N-type semiconductor material. Okay, so this is taken, an N-type semiconductor material is taken, and then two P-type junctions are diffused on the opposite sides of its middle part. So these junctions form the two PN junctions or the gates, okay? And the area between this gate is called the channel. So for example, this is the narrow bar of an N-type material. Okay, so what are we going to do is that we are going to diffuse a P-type material. So I will be getting a P-type material. So I will be diffusing that, or I will be, what do you mean by diffuse? Okay, I will embed that on the opposite sides of my I will be embedding that on the opposite side of my narrow end band material. So this is the N channel. So this is the N type material, and this two produces the gate. Okay, so since this gate is just the same, it will be redundant if I will be having two terminals for this gate. So since these gates are just the same, so I will just get one side, okay, of this, and I will be calling that the gate. Now, this center here, so the center area here, so this forms two PN junction diodes. So what are those PN junctions? So this is P type, So this is P-type, N-type, N-type, and P-type. So I will be having an 2p-n junction. Okay, so these are the gates. I have two gates here, and the area between the gates, I will be calling this channel. So since this is N-type, so I will be calling this an N-type or an N-channel JFET. Okay, so this is how it looks like. Unlike with the BJT, if you will remember how we created or how we fabricated your BJT, we have here your N-type material, we have here your P-type material, and then we have here another N-type material. So it formed two PN junctions. So this is your first PN junction and this is your second PN junction. But, so this is the emitter, this is the base, and this is the collector. The difference here is that the emitter, although the emitter and the collector, they are both made of same N-type material, but the doping for this N-type materials is different. So emitter is most heavily doped compared with the collector. So for the JFET, what we have here is that we get a strip of an N material. So this is your N material, and then we diffused, okay, a P-type material on the sides. So this is now your gate and this is now your N channel. Okay, so that is the difference. Although they both have two PN junctions, since this is P, this is N, and this is N, and this is P. But look at the difference. So the difference here is that your N material is just the same. Okay, so it is not differently doped. Okay, so we call this the channel. So if we use P-type material instead, so we have a P channel. So if we use an N-type material, so we have an N channel. Okay, so this is how your JFET looks like. So we have here your N-type, and you have here, so this is your entire N channel, and then this is your gate. Okay, so this is your symbol. So technically, we are pointing at the N-type material. So the arrow points at the N-type material. So for N channel, your arrow is pointing inside because this is the N material is inside your bar, while for P channel, it is pointing outside because your N material is somewhat outside your bar. Okay, so this is for an N channel and this is for a P channel. Okay, so we have three different terminals. We have the gate, which is your P-type material. Okay, so although this two is connected, we only have one terminal for the gate. And then we have the drain and we have the source. Okay, so what is the difference between so the emitter and the collector is somewhat like your drain and your source, and your base is somewhat like your gate. But the difference here is that the drain and the source can be interchanged. So why can we interchange it? Because technically they are made up of the same material. So one time we can use this is the drain and this is your source, and the other we can just exchange the terminals because technically they are the same material. Okay, so this is your N-channel JFET and this is your P-channel JFET. So the two regions are internally connected and a single LED is brought out, which is called the gate terminal. So the gate terminal is the one which is different. Okay, so ohmic contacts are made at the two ends of the bar. So we call the N-type material or the N channel, we call it a bar. So ohmic contacts are made at the two ends of the bar. One LED is called the source terminal and the other is the drain terminal. So what are the three terminals for JFET? So we have the gate, we have the source, and we have the drain. So when potential difference, so what do we mean by potential difference? When we apply biasing, okay, when we apply source voltage. Okay, so when potential difference is established between the drain and the source, current flows along the length of the bar through the channel located between the two P regions. So as you can see, Okay, so since this is an n-type material, what is the majority carriers for n-type material? So the majority carriers for n-type materials are the electrons. So the electrons, upon application of potential difference, they are, okay, so current flows along the length of the bar. Okay, so through the channel located between the p regions. So the electrons from the source are what? Being carried out. Okay, so they will be flowing from the source. So this is your source going to the drain. So as you can see, the electrons, purely electrons, will be flowing, okay, or will be moving from the source going to the drain. So this is why we call this a unipolar device. So why unipolar device? Because upon the operation of your transistor, where is your current flowing? What type of majority carrier is present? So the type of majority carrier that is present is just your um, electrons. Unlike for BJTs, okay, so BJTs are bipolar because the electrons here, okay, the electrons here, for it to flow from the emitter going to the collector, they need to pass through the base. And what are the majority carriers at the base? We have holes here. So therefore, both the electrons and the holes are being utilized in the proper operation for your BJT. So that's why it is called bipolar. But as you can see, the holes at the gate, okay, will not mingle. So they will not interact with the electrons from the source going to the drain, because technically it will be passing only through the channel. So that is the reason why this is called unipolar and this is called bipolar. Okay? So the current consists of only majority carriers. It's either for N channel, is it just consists of the electrons. For p channel, they're just made up of the holes. Unlike for BJTs, we have the majority carriers and the minority carriers. Okay, so the source, it is the terminal through which majority carriers enter the bar. Okay, so the drain, it is the terminal through which majority carriers leave the bar. Okay, so it is like your source is your emitter and your drain is your collector. Okay, so it is the terminal in which the majority carriers leave the bar. The drain to source voltage, or VDS, drives the drain current. Actually, we only have one current involved in JFETs, and that is the drain current. Why? Because as you can see, your drain current is just the same. Okay? So since we are only passing through a same channel, your drain current is just the same as your source current. So we will just be using the drain current for both of them. Okay? So the drain to source voltage, or the VDS. So again, it applies when we have a capital letter for as your what do you call this, for DS. So this means that the positive terminal is connected at the drain and the negative terminal is connected at the source. Okay, so or the drain is positive with respect to the source. So your voltage VDS. So this is the counterpart for the VCC. Okay, for the VCE in the BJT. Okay, so the VDS drives the drain current ID. So the gate, these are two internally connected, heavily doped. So what do we mean by heavily doped? So these are the two internally connected, heavily doped impurity regions which form two PN junctions. Okay, so the gate to source voltage, or the VGS, reverse biases the gates. So our VGS must reverse bias your gate. So later on with the circuit, we will look at how are we going to place our sources so that your gate is always reverse biased. Now, do you still remember what happens when we have a reverse bias condition? So that means we are not allowing any current to pass through the gate. Okay, so technically, we are going to make your GIG or your gate current be equal to 0. How? By reverse biasing your VGS. Okay? So what is the channel? Channel, it is the space between two gates through which majority carriers pass from the source to drain when your VDS is applied. So there are two theory of operation. Okay, so we have if you still remember in BJT, how do we connect your BJT so that it will be operating at the active region. So first, the emitter to the base junction must be forward biased, while your base to collector junction must be reverse biased, if you can still remember that. So for JFET, this is how are we going to connect your JFET so that it will be operating as an amplifier. So first is gates are always reverse biased. So since gates are always reverse biased, hence your gate current IG is practically 0. So technically speaking, what are the currents involved here? So you have your IG, you have your ID, and you have your IS. Okay, so what happens is we're going to set your IG always equal to 0. So in IB, you still remember our base current. Base current is approximately equal to 0, but it is not equal to 0. So it is very, very small in microampere range compared with the IC and your IE. So the difference between BJT and FET is that your in BJT, IB is very, very small in microampere range. However, in FET, in JFETs, IG is practically equal to 0. Okay, so we're going to reverse bias your gate so that we can have your IG equal to 0. And then for BJT, we said that IC is approximately equal to IE. But in JFETs, we have here ID is equal to your IS. So technically speaking, we only have one current involved here. So what is that current? That current is just your drain current. Unlike for BJT, you have IB, you have IC, and you have your IE. Okay? And then, the second theory of operation is that the source terminal is always connected to the end of the drain supply, which provides the necessary charge carriers. So you might be confused since the drain and the source, they are of both material, so they are both N-type. Where are we going to place the positive? Where are we going to place the negative source? So the source terminal is always our basis, okay, for the polarity of your DC source. So the source terminal is always connected to the end of the drain supply, which is your VDD, the counterpart for your VCC in your BJT. So connected to the end of the drain supply, which provides the necessary charge carriers. Okay, so you have to remember this two basic theory of operation. Okay, so if we're going to wait. So for example, let us apply your biasing. So we have here an N channel. So we have here your N channel. So your drain. This is your drain and this is your source, and this is our gate. So since this is an N channel, so therefore your gate is P-type. Okay. So how are we going to apply this theory of operation? So your gate must always be reverse biased. So what do we mean by this? So since this is P-type, we are going to apply here the negative terminal and we're going to apply here the positive terminal. So applying the negative terminal to the p-type material and the positive terminal to the n-type material here, this will cause a very, very large depletion region between your gate. So therefore, what happens when we have a reverse bias and great depletion region or wide depletion region, that makes your IG practically equal to 0. So no gate current will be entering your bar or your channel. So technically, the current that will flow here is just dependent on the electrons or the majority carriers of your N channel. Okay, understand? Now, how about here? Okay, so the second theory of operation is that what how are we going to connect your positive and negative since they are both n-type material? So where is positive, where is negative? We will be dealing with the source. So where is the source? Here is the source. And we need to forward bias it for current to flow. Okay, so since this is n-type, how do we forward bias your n-type? We should connect the n or the negative terminal here so that it will be supplying your electrons. Okay, so it will be the source of your electrons. And of course, the positive is this one. Okay, so again, the current flow is opposite with the electrons flow. So the electron flow is from the source. So these are your electrons. So your electrons will be flowing from the source going to the drain, while your current flow will be what? Will be dictated by your source here, which is from negative to the positive. So, which is your ID. So, the drain current is from the drain going to the source, while the electron flow is from the source going to the drain. So, we need to place your negative terminal here so that we can supply many electrons at your source terminal. So, this is how you place the biasing to satisfy this two theory of operations. Okay? So, we have different conditions here. When VGS is equal to 0, so this is your VGS, the voltage between the gate and the source is equal to 0. And VDS, this is the voltage between your drain and your source. When they are both equal to 0, in this case, your drain current is equal to 0. Okay, so it is just like placing your JFET in the table, on top of a table, and then you have no sources connected to it. So, of course, we do not expect it to function. Okay, so therefore, when your VGS is equal to 0, that means your VGG, so we call this your VGG and we call this your VDD. Okay, so when we do not have any VGG and VDD here, therefore, we expect that ID is equal to 0. Okay, so the depletion regions around your PN junctions are of equal thickness and they are said to be symmetrical. Okay, now, what happens when VGS is equal to 0? Okay, so when this is equal to 0 and your VDS is increased from 0. So what do we mean by increased from 0? We are applying a positive source to your VDS. So the JFET is connected to the VDD. So this is your VDD. Okay, so the electrons flow from the source going to the drain, whereas conventional current ID flows from the drain going to the source. The gate-to-channel bias at any point along the channel is equivalent to the VDS plus VGS. But since the external bias VGS is equal to 0, gate channel reverse bias, the gate channel reverse bias is provided by the VDS alone. So what happens is, since the value of VDS keeps decreasing as we go from the drain to source, the gate channel bias also decreases accordingly. So it's if you're going to imagine, just imagine, okay, you have a resistance, entire resistance at the middle. So every time you have here your current, what happens? You have a voltage drop. Okay, so you have a voltage drop. So every time it goes down, the source VDD is what? Somewhat subtracting. Okay, so it has a maximum value at the drain gate region. It still has a greater value here and a minimum value when it comes to the source gate region. So depletion regions penetrate more deeply into the channel in the drain gate region than in the source gate region. So as VDS is gradually increased from 0, ID increases proportionally as per Ohm's law. Okay, so the ohmic relationship between VDS and ID continues till VDS reaches a certain critical value. So as we increase your VDS, okay, as you increase your VDS, your ID increases proportionally. So if this is a same or a constant resistance, so if this is a constant resistance, what is our ID equal to? ID is equivalent to V all over R. So if we make this R constant and we keep on increasing your V, so what happens is your I keeps on increasing. Okay, so it will keep on increasing, increase this will increase until it reaches a critical value. So we call that critical value as the pinch off voltage. Okay, when your drain current becomes constant at its maximum value. So that maximum current is what we call your IDSS. So IDSS is called the drain current. This is the drain current, okay, when what is missing? IDSS. So ID, so the gate is missing. When the gate, so this is IDS, what is missing? The gate. When your gate is shorted. So how did we know that the gate is shorted? Because we said earlier that VGS is set to 0. So the maximum current can only occur when your VGS is equal to 0. When your VGS is no longer equal to 0, so that is a different story. Okay? So the maximum current is called IDSS. This is the drain to source current when your gate is shorted. That means your VGS is set to 0. So we call this critical value as pinch off voltage. Why? What happens inside your FET? So what happens inside your FET is a phenomenon wherein your resistance here is being elongated. So of course, we cannot see this with our naked eye, but it happens that your resistance here is somewhat being stretched. So what happens when your wire is being stretched? So that when the length of the wire is being stretched, that means the resistance is also increasing. So what happens is that when your resistance increases, even though you increase the voltage, somewhat your current becomes constant. Okay, because an increase in voltage causes an increase in resistance, so the increase is just being cancelled out, therefore your ID is just being held constant. Okay, so this is what we say, this is the occurrence of your maximum current or your IDSS, and it happens only when your VDS reaches a critical value. So don't forget that critical value. This is called the pinch off voltage or your VP. Okay, so other books they call this VPO, other books they just call this VP. So when VDS is increased beyond VPO, what happens? Your ID remains constant at its maximum value, which is IDSS, up to a certain point. So further increasing this more, ultimately, a certain value of VDS called VDSO, okay, is reached when JFET breaks down and ID increases on to an excessive value. So since IDSS must be the maximum value, so upon increasing it, that means the end of life of your JFET. So we have to take note of this. Okay, so when this happens, your JFET already is broken, so it breaks down. So this is the story. Okay, so upon increasing, okay, when this is set to 0, this is shorted, so increasing this out, so the current increases until it reaches a pinch off wherein your resistance here is somewhat being elongated, although you do not look at the JFET and then, oh, it's getting longer. No, it's happening inside. Okay, and finally at its breakdown. Okay, so what happens when your VDS is equal to 0 and your VGS is decreased from 0? So what do we mean by decreased from 0? So we are further increasing the reverse bias for this VGG. So in this case, as VGS is made more and more negative, the gate reverse bias increases, which increases the thickness of the depletion region. Okay, so the channel is said to be cut off. Okay, so the value of VGS, which cuts off the channel and hence the drain current. So since if we increase that, so what happens is that, so this is your P channel. So it increases, the depletion region increases until your electrons cannot move anymore from the source going to the drain. So the channel is said to be cut off because there is no more channel for the movement of your electrons. So the value of VGS, which cuts off the channel and hence the drain current, is what we call the VGS off. Okay, so that is your um, VGS, which cuts off your channel. So what happens is like this. Upon further increasing your reverse bias here, so the depletion region widens and widens until it closes the channel already. So when the channel is closed, where is your current flowing? So where will be your current flow? So no more. So therefore, in this case, your ID is equal to 0. Now, when VGS is negative and VDS is increased, the values of VP as well as the breakdown voltage are decreased. So this is what is happening, class. When your VGS is equal to 0, so this is your VGS. When your VGS is equal to 0, this is the maximum current. So upon upon increasing your VDS, it will increase, it will increase, it will increase until it reaches a certain critical maximum value called the IDSS. So that is when VGS is equal to 0, and then it will remain constant until it breaks down. Okay? Now, what happens if you have a negative 1 VGS, for example? So your maximum current cannot be what? Equal to your IDSS anymore. So the effect of your VGS is it will minimize your current. Okay, so upon making your VGS more negative, the maximum current possible will be smaller and smaller. So as this gets more negative, the maximum current becomes smaller until it reaches your VGS. So when your VGS reaches your pinch off voltage, that is the time when your current is equal to 0 already, because the channel is being closed and current cannot be passed anymore. Okay, so this is also the reason why it is called a voltage control device. So why is it called voltage control device, class? Because what controls your current here? Your current is being controlled by your VGS. So the VGS dictates whether your current will be reaching its IDSS or whether your current will be smaller. So since VGS is a voltage source, so JFETs are called voltage controlled devices. So what controls your current ID is your VGS. Okay? So we have static characteristics for a JFET. So we call this as your drain characteristics. It gives the relationship between your ID and your VDS for different values of VGS. And then we have a transfer characteristic. So it gives the relationship between ID and VGS for different values for VDS. So this will be very helpful in analyzing the DC circuit for JFETs. Okay, so later on our next videos, we will be discussing the DC analysis for JFET. So drain characteristics and transfer characteristics will be very helpful because technically we will be using graphical solution for those. Okay, so this is just like what we did in your look, the arrow is being included in the gate. So the drain and the source, they don't have any significant differences because technically by its construction, by its devices, or by its components, drain and the source are made up of technically the same type of material. Okay, so the voltage between your drain and the source, this is your VDS. So if you're still remembering in your BJT, so this is just like your VCE, and then your VGS here, so this is just like your VBE. Okay, but here we call this your VGS. So how do we reverse bias your VGS? So your VGG must be, so the negative must be connected to the P-type. So how do we connect your VDD here? So the negative terminal must be connected to the source so that we can supply more and more electrons here. Okay, so JFET drain characteristics, when VGS is equal to 0, it is divided into 3 regions. So we have the ohmic region, we have the curve AB, and we have the pinch-off region, which is also known as the saturation region. And then later on, we have the breakdown region. Okay, so we have here the first type when we are increasing your VDS while your VGS is equal to 0. So just like Ohm's law, so ohmic region, it increases. So as you increase your VDS, likewise your current also increases until it reaches a certain point, or the pinch off region, wherein it the current, even though increasing your VDS more, however, it will be what? Saturating. So what do we mean by saturation? So your current will be of a same value, so it will remain constant, and the value is equivalent to IDSS. Always remember, IDSS is only possible when your VGS is equal to 0. So this is what we call the pinch off or the saturation region. So furthermore, increasing your VDS, what happens? Your current increase more of your IDSS. So when this happens, this is already the breakdown region for your transistor. Okay, so this is the JFET characteristics with external bias. Pinch of voltage is reached at a lower value of ID than when VGS is equal to 0. So as you increase your VDS, your current slow is being held lower values until it reaches 0. So when it reaches 0, that means your VGS is equivalent to your pinch off voltage. Okay, so when your pinch off voltage is equal to your VGS, your current becomes 0. So this is the transfer characteristic. So this is what we call the Shockley's formula. So we only have one formula for JFET, and this is the Shockley's formula, and this shows the relationship between your ID with your VGS. Okay, so this is your ID, the y-axis is your ID, so this is positive, and then VGS, as we all know, is negative, so this is for N channel. For P channel, the transfer characteristic is at the other side, because for you to reverse bias the gate, you need a positive source. So this is for an N channel. Okay, so this is your IDSS. IDSS is only possible when your VGS is equal to 0, and then ID is equal to 0 when your VGS is equal to your VP. Okay, so it happens like this. By the Shockley's formula, using the Shockley's formula class, so your ID is equal to IDSS 1 minus VGS all over VP squared. Okay, so as you can see, when your VGS is equal to 0, so this is 1 minus 0, so this is just equal to 1. That is the time when your ID is equal to your IDSS. Okay, now, when your this is VGS, when your VGS is equal to VP, okay, so this is equal to 1. So 1 minus 1, that is 0. Okay, multiplied by IDSS, so that is when your ID is equal to 0. So that is two important points to look at too. Okay, so this happens when your when your VGS is equal to 0, and this happens when your VGS is equal to your VP. Okay, now, Um, what is always given in the specification sheet? How can we draw the transfer characteristic curve? Okay, for a certain JFET class, IDSS and VP are always constant. Okay, so they are constant. So therefore, we can only vary your ID upon varying your VGS. So this is called a voltage controlled device. So why is it called voltage controlled device? Because your ID is being controlled by your VGS here. Okay? So let us now go to the second type, which is the MOSFET or the IGFET. Okay, so, excuse me. Okay, so we have here MOSFET or IGFET. So this is the second type of FET. Okay, so the first type is the JFET. So the second type is the MOSFET or the IGFET. So there are two types of MOSFET or IGFET. We have the Depletion-Enhancement MOSFET or the DMOSFET. So it can be operated in both the depletion mode and the enhancement mode by changing the polarity of your VGS. Okay, so for JFET, we always make your VGS reverse bias. Why? Because the number one rule is that we have to make IG be equal to 0. So, when we say depletion mode, we are going to make your VGS reverse bias. However, enhancement mode, we are going to make your VGS forward bias. So, if it is forward bias, therefore, how are we going to make IG is equal to 0? Okay, so this is known normally as, this is also known as the normally on MOSFET. So, why? So, for the construction, it also has a source, a gate, and a drain. Okay, but its gate is insulated. Okay, so from the symbol, look at the symbol, the gate is insulated. So, you have an insulator at the middle. So, that insulator is an ultra thin metal oxide insulating film. So, what does an insulator do? So, an insulator hinders the flow of current. So that is why we can have your VGS forward bias, because even though we produce IG, we don't have a problem because the gate is insulated. That means the current IG cannot penetrate to your channel. That's why it is okay for us to have a positive or a negative VGS, okay? Because the gate is insulated. So this is how it is constructed. So why normally on? Because even though we don't have VGS here, there's still a proper path, okay? There's still a complete path from the source going to the drain. Okay? So the electrons, okay, the electrons can still pass through the electrons can still this is the electrons, the so this is your n channel. The electrons can still pass through from the source going to the drain. Okay, so as you can see, the third terminal here, sometimes it is called a body. Okay, so we have here what we call a body. So, working in the depletion mode, so for the depletion mode, the DMOSFET behaves just like a JFET. Okay, so what do we mean by it's just like a JFET? So, we just place a positive we have a negative VGS here. Sorry, this is for a, um, For this is for a enhancement mode. So the depletion mode, it is just the same as what we have discussed in JFET. So for the enhancement mode, okay, so for the enhancement mode, we can see that we can place a positive terminal here. So positive, so the negative is being connected at the negative or the source, which is the negative terminal. So what happens is the electrons is not only being supplied by your VDD here, but it is also being supplied by your VGG here. So what does it means is that we have more electrons flowing from the source going to the drain. So what is the implication? So if you have more electrons flowing from the source going to the drain, that means we have higher current, we have higher drain current compared to the enhancement, compared to the depletion mode type. So since they are just the same, they both use the Shockley's equation. Okay. However, look at the difference. This is your depletion mode. So the depletion mode is, it happens when the IDD is, when your VGS is equal to 0, you have your IDD here. So when your VGS is increasing negatively, your ID is um, getting smaller and smaller until it becomes 0 when it reaches your VGS off. So this is the depletion mode. So just like the JFET. Now, what is the enhancement mode? In the enhancement mode, we can now apply positive VGS. And when you apply positive VGS, what happens? You can now have a current which is greater than your IDSS. So in JFET, we don't have current greater than IDSS. But in the MOSFET, we have a current which is greater than your IDSS. Okay? So just like this one, so IDSS occurs when your VGS is equal to 0. ID is equal to 0 when your VGS is equal to your VGS off. So this is your depletion mode. Then the difference is upon applying an enhancement mode or a positive forward bias. So what happens is that you have a current which is greater than your IDSS. So the DMOSFET is the same with the JFET at the depletion mode. So the difference is the possibility of getting a higher current than your IDSS upon application of your VGS. So why can we apply positive VGS? Because the gate is now insulated. So we do not worry if we have a gate current because your gate is now insulated. So therefore, we can have a positive or we can have a greater current than IDSS. Okay? Now, the second type of MOSFET is the enhancement only. So what do we mean by enhancement only? So this is also called the normally off MOSFET. So this operates only in the enhancement mode. So that means it must be forward biased only and has no depletion mode. So depletion mode or the reverse bias mode is not permitted. So it not only positive gate voltages, but it works on a large positive gate voltages only. Okay, why? Because in e-MOSFETs, there exists no channel between the drain and the source. So you still remember on the second slide, the drain and the source are connected using a broken lines. So the broken lines there signifies that there is no direct connection between the drain and the source. So what is the symbol for your e-MOSFET? So this is our symbol for your e-MOSFET. Okay, so um, the source and the drain is not connected. Therefore, the electrons cannot pass from the source going to the drain. So what do we need is we have to apply a positive or a forward bias at the gate so that we can connect this two by making the depletion region smaller. Okay, so it happens only when we have a large forward bias at the gate. So it is called e-MOSFET or the normally off. Why normally off? Because we cannot function without your VGS. So VGS is very, very important. So this is our formula for MOSFET. So both D MOSFET and JFET uses the Shockley's formula or the Shockley's equation, while MOSFET uses this equation. So as you can see, we cannot function unless your VGS here is greater than your VGS TH. Okay, so the VGS TH is the voltage required for the depletion region to be penetrated. Okay, so you have to have a greater VGS here. So when your VGS is greater than your VGS TH, that is the only way that you can have your ID here. Okay, so this is the transfer curve. Look, we do not just require a positive VGS, but we require a higher positive VGS. Okay, so why enhancement only? Why cannot use depletion? Because if you further increase this negatively, so what happens to your drain and source? So technically, the depletion region will be what? More wider. So when it's more wider, well, it's wider, that means the drain current is not possible to pass. Okay? So these are the transfer characteristics. So for BJT, this is your controlling variable and this is constant. So therefore, your current here is being controlled by our current here. That's why BJTs are called current controlled devices. While for FET, this is your control variable, okay, and this is your constants. IDSS and VPR constants. So VGS, which is voltage, is controlling your ID here. So therefore, this is called a voltage controlled device. Okay? So as you can see, BJT linear, more on linear because we don't have a square in your formula. However, here we have a curve. So why do we have a curve? Because we already have here a squared. So our graph here is not a straight line anymore, but more of a curve. So obtaining the transfer curves from the drain characteristics. So this is your transfer curve and this is your drain characteristics. So when VGS is equal to 0, that is your IDSS. When your VGS is equal to -1, so your ID somewhat becomes smaller. Every time this goes more negative, your current becomes more smaller until it reaches 0 when your VGS is equivalent to your VGS TH. Okay? So, but what is more important in the DC analysis is the transfer curve. So we have to determine or we have to study how to draw or how to obtain the transfer curve. Okay? So applying Shockley's equation, your transfer curve is obtained directly from the Shockley's equation. So IDSS and VP, they define the limit of the curve on both axes and leave only the necessity of finding a few intermediate plot points. So if you can already get the curve just by using these two, then it's okay. But sometimes we need an extra point so that our plot is more accurate. Okay? So when your VGS is equal to 0, substituting that to your formula, that is your ID is equal to your IDSS. Okay? So just like this one, for example, in drawing that, okay, so you already have 2 points. So first point is your IDSS when your VGS is equal to 0, and your second point, which is your ID, is equal to 0 when your VGS is equal to your VGS TH. Okay, so if you can already draw your curve using this one, then it's fine. But if you want a more accurate curve, we can have few more additional plot points. So we can use this formula, VGS, for a given level of ID. Okay, so VGS is equivalent to, upon manipulating the formula, VGS is also equal to VP 1 minus the square root of ID all over IDSS. Okay, so shorthand method, transfer curve. So this is plotted so frequently, so therefore we can make use using the formula. When your VGS is equal to 1/2 of your VP, your ID is equivalent to IDSS all over 4. Okay, so that this happens when your VGS is half of your VP. So this is your VGS is equal to your VP. So when your VGS is equal to half of your VP, so let us say this is your half of your VP, your ID is equal to 1/4. So if this is 1/2, so this is 1/4. So this is 1/4. So sometimes you have a point here. Okay? Another is when your IDSS is 1/2. So this is your 1/2. Your VGS is approximately equal to 0.3 of your VP. So if this is your VP, divide this by 3. So this is your 0.3 of your VP. Okay, so using these 4 points, we can draw your plot. Okay, so sometimes we use this transfer curve frequently. Okay, so summarizing this is your 4 points. So what are your 4 points? So when your IDSS is equal to 0, your VGS is equal, when your VGS is equal to 0, this is equal to IDSS. When your VGS is equal to 0.3 of your VP, this is half of your IDSS. When your VGS is equal to 0.5 of your VP, this is 1/4 of your IDSS. And when your VGS is equal to VP, this is equivalent to 0. So upon plotting these 4 points, we can actually draw your transfer characteristic curves. Okay? So, for example, we have here the transfer curve defined by your IDSS. So, let us say, for example, when your IDSS is equal to 12 milliamps and your VP is equal to -6. Okay? By applying the 4, okay, by applying the 4 formulas here, we have VGS, okay? So this is equal to your IDSS. When this is equal to 0, so this is your IDSS. So when this is equal to 0.3 of your VP, this is equivalent to IDSS over 2. If this is 0.5 of your VP, this is IDSS over 4. And when this is equal to VP, this is equal to 0. Okay, upon applying this one here, so when your VGS is equal to 0, you have your IDSS. So this is your first point. Okay? So when your 0.3 of VP, so what is 0.3 of 6? So this is 2. Okay? So that is 2. So this is your 2. And then half of your IDSS, so this is 6. So the intersection of your 2 and your 6, that is your second point. Okay? So 1/2. So what is 1/2 of -6? So -3, that will give you 1/4. So what is 1/4? So that is 3. So this is your 3 and this is your -3. So this is your next point. And last is your VP is equal to -6. So your ID is equal to 0. So upon plotting those 4 points, you can now draw the curve. Okay? So why is this important? You will be using this on our DC analysis. So we just need to practice so that when we discuss the DC analysis, you know already where does this graph came from. Okay? So for a MOSFET, what happens for a MOSFET? So for a MOSFET, possible current which is greater than IDSS is already what? Possible. Okay? So we can form the 4 points. So where is your 4 points there? So your 4 points there is, first, when your VGS is equal to 0, your IDSS is equal to 10. Okay? And then, when your VGS is 0.3, so what is 0.3 of 4? 0.3 of 4 is, let's compute. What is 0.3 of 4? 0.3 times 4 volts, so 1.2. So where is your 1.2? Roughly here. So that is half. So 5, this is your next point. And then, what is your half of 4? So that is 2. So this is 1/4. So that is 2.5. This is your next point. And then this is your 0 point. So the difference for a MOSFET N channel is that we need one more point. Okay, so what do we do with the one more point here? So if this is 1, we don't have any choice. We don't have any shortcut. But we will be using the what? We will be using the Shockley's formula. So you really need to solve. ID is equal to what? IDSS multiplied by 1 minus VGS. But what do? We have to make your VGS positive. Okay, so we have one point wherein your VGS is positive. So we have your positive 1 volt all over negative 4 volts. So where is the negative 4 volts? This is your VP, and then IDSS, this is 10 milliamperes. Okay? So then we have a square there. So using this formula, okay, solving for that formula, we have a value which is approximately 15 point something. Okay? So upon computing for this, you have a value which is 15 point something here. So that is your fifth point. So connecting your 5 points here, you can now draw the curve. So this curve is very important. We will be using this in our next video. Okay, so for e-MOSFET, okay, for e-MOSFET, we have a different curve because we will not be using the Shockley's formula here, but we will be using this formula. K is a constant that is a function of the construction of the device. K is ID on, we have VGS on minus VT squared. Okay? So, this is the transfer characteristic. It should be positive. Must be a large positive value. Okay? So, sketching the transfer characteristic for an N-channel enhancement type MOSFET using the drain characteristic. So, for example, this is our K, 0.5 times 10 raised to negative 3 or milli. So, our VGSTH here is negative 4. So, what we do is we draw a horizontal line at ID until it reaches VT. Okay, so we don't have current until it reaches your VGSTH or your threshold voltage. So, your current will be starting when you have a VGS which is greater than your VGSTH. Okay? Applying, so a level greater than VT is chosen. So let us say 5. Okay? So if you have 5 there, so that is 5 minus 4, so 1 times 0.5. So that will give you around 0.5 milliamperes. Using 6, so 6 minus 4, so you have 2, okay, 2 times squared, okay, so 4 times 0.5, so that will give you 2. And then 7 minus 4, so 3, then squared, so 9, multiplied by 0.5, so around 4.5, and then so on. So it's up to you if how many points do you need. So this is how you draw the transfer characteristic for an enhancement MOSFET. Okay, so we will be doing this. We will be using this as we go on with our DC analysis. But for now, I will just stop here, and our next video will be about the DC and AC analysis for FETs. Okay, both JFET and MOSFET. Okay, so you can read. You may read your textbook. It's included in Wilestad. If you have any questions, just message me so that I can answer your questions. Okay, so wait for the next video. So the next video will contain the DC and the AC analysis for field effect transistor. Okay, so I hope you understood the lectures. Have a nice day and God bless. Bye.